Hello everyone, my name is Human Zarenkoop. I'm the product manager for the wireless product in MathWorks, including 5G, LTE, wireless LAN, and communications toolboxes. And it is my pleasure to welcome you to this MathWorks webinar entitled 5G Beamforming Design. Let's go over the agenda of this presentation. After some introductory remarks, I essentially going to present five different sections related to 5G beamforming. The first section is all about 5G waveform generation. The second topic is all about channel modeling and pre-coding. When you are working with beamforming scenarios, you have to be aware of the effect of channels on propagation environment, and you also have to design pre-coders that spatially direct your transmissions. Which brings us to the third topic, the antenna array design and the MATLAB tools we have to not only design antenna elements as well as antenna arrays that help with characterizing your beamforming performance. Another topic is hybrid beamforming. The complexity and the power consumption of a fully digital beamforming can be mitigated by using hybrid beamforming approaches that divide the beamforming into two modes. In some direction is the analog, and in some direction is the digital approach. Finally, you have to design the RF front end in order to improve your performance. And for that, we have tools in MathWorks that help you characterize the power amplifiers and design DPDs and other elements that related to RF transmission chain. Finally, I'm going to provide some summary. Let's go over the enabling technologies of 5G. As you know, 5G has multiple use cases, and one of the most familiar use cases is the 5G, enhanced mobile broadband, and that is the challenge that the networks that are going toward 5G is dealing with right now. How do we substantially increase the throughput and data rates over our mobile communications network? So among technical solutions that have been proposed is the following. You can increase the bandwidth by using a signals on larger bandwidth. You can essentially increase your throughput. And you can also squeeze more from a given hertz of bandwidth. That's called better spectral efficiency. You know, how much more bit per second can you use per hertz? You can also use flexible air interfaces. In this case, it means using multi-carrier communication systems that use OFDM, OFDMA, and multi-user MIMO. And also you can use small cells such that you can essentially use MIMO techniques to achieve better received power and performance. Another approach is also using higher frequency band, and that's one of the main themes that 5G will exhibit. And instead of working at the typical below 6 gigahertz frequencies in the 4G and before cellular communication systems, we're going beyond 6 gigahertz, millimeter wave. And by using that, you have large swaths of bandwidth available for you, and you can essentially achieve the high throughput you want. Now, all these things are not without challenges. The minute you decide to go to millimeter wave and higher frequencies, the signal attenuation becomes a real problem. Systems with very broad bandwidths, the frequency selective fading becomes a real problem. And then you have to seriously look at multi-carrier systems like OFDM, OFDMA, and channel estimation and equalization in order to combat the effect of frequency selective fading. And also you need scatter-rich propagation environment in order to make these MIMO OFDM systems possible. And then you have to constantly update your channel characteristics, and your channel models. How to put it all together? You're using high carrier frequencies, larger bandwidth, and large antenna arrays. This is an approach that works with 5G, especially at millimeter wave. This is known as massive MIMO. And massive MIMO essentially means that you're using very large antenna arrays in order of much above 64, 128, 256, and so on. And remember that if you are doing all digital beamforming on these large antenna arrays, behind every antenna that transmits the signal, there is an RF and analog chain, wideband chain that requires a large amount of power and complexity. So in order to mitigate the power and dissipation problems of these massive MIMO systems, hybrid structures have been proposed to achieve the best compromise. As you can see, in what we envision, the massive MIMO technology of the future, the transmitter has narrow beams that targets each individual receiver. That's in multi-user MIMO scenarios. That requires large antenna array to achieve essentially narrow beams. And we don't have those kind of transmission in all direction isotropic anymore. We are doing focused transmission. And in order to achieve that, you need to essentially coordinate your pre-coding and beamforming together with RF chain such that you can custom design transmission to different users at different narrow beam angles. So what is the workflow for such hybrid beamforming 5G architectures? You need to generate a waveform. These waveforms essentially determine how much bandwidth you're using, and there's a lots of flexibility in there in 5G. I'm going to talk to you about that. You have to design antennas and antenna arrays that enable you to achieve those narrow beams that participate in the process of multi-user MIMO, massive MIMO structures. You have to have a representative channel model with lots of scattering included in order to make the essential estimation of the angle of arrival, angle of departure, the locality of the transmitter and receiver, all of that possible. And based on that, if you want to use spatial multiplexing and send multiple streams on different antenna ports, you have to compute the pre-coding matrices, which are the digital beamforming requirement. The digital pre-coding matrices that multiply weights to the digital beamforming architecture in order to steer your signal digitally to the direction that you want. And if you are doing high beamforming, you also have to consider the analog beamforming parts, those elements that use phase shifters in order to essentially steer in the analog context without using all the RF chain to steer your beam in another direction. And after all of that is done, you have to consider the effect of the RF front end, the amplifiers, the filters, and so on, and make sure that within your bandwidth of interest, the amplification is linear. Otherwise, you suffer a lot. So all of these considerations, which we call system level design considerations, come into play to produce a successful 5G high beamforming architecture. Let's talk about the first element, the 5G waveform generation. 5G standardized in 2018, and in MathWorks we have introduced our 5G toolbox, our MathWorks product that allows you to model, simulate, and test 5G systems in the same year, 2018. One of the characterizing features of 5G technology is that it is based on OFDM. However, unlike 4G, where the subcarrier spacing or the resolution in frequency were constant. In 5G, the subcarrier spacing of the resolution and frequency is a variable. So your difference in frequency between two subcarriers can be 15 kilohertz or multiples of 15 kilohertz that are power of 2, 30, 60, 120, and so on. Now, we have a duality between time and frequency, which means that if your subcarrier spacing or sampling is short, the duration in time is long. So for 15 kilohertz, 1 millisecond slot in time, and as you increase subcarrier spacing, the slot in time reduces in size. But you know that the minute that we use multiple of subcarrier spacing, we achieve immediately higher bandwidth. So if you send the same information over a 15 kilohertz subcarrier, you are at a 50 megahertz, if you like, bandwidth. But by doubling the subcarrier spacing, you are occupying essentially 100 megahertz. These are the considerations that show the flexibility of 5G in terms of time frequency resolution. And these are the type of waveforms you have to generate in order to test and validate your 5G and 5G beamforming designs. As I mentioned, the 5G toolbox supports both uplink and downlink 5G waveform generation. And as you can see, the generated waveform in 5G toolbox essentially allow you to have mixed numerologies, signals and waveforms of various subcarrier spacing, multiple bandwidth parts, each bandwidth part associated with different user or UE, multiple physical downlink or physical uplink shared channels. They're all fully parameterizable and allow for the synchronization signals and bursts, SS bursts, that are needed to synchronize everything in 5G. I'm going to show you with a very easy to use app called Wireless Waveform Generator app, which has been introduced in our tools ever since 2018 B release, how easy it is for you to generate 5G waveforms. Now you're going to test your wireless designs interactively, essentially using an app by clicking the right parameters. Even if you're not a proficient MATLAB programmer, you can interactively parameterize and generate 5G waveforms. And the waveforms, the IQ samples that are at the baseband, you can actually see the MATLAB code that generates them, and you can transmit them over the air right from MATLAB environment if you're using an RF instrument that connects to MATLAB. Let's go to MATLAB and take a look at this app known as Wireless Waveform Generator app that makes the process of 5G waveform generation very easy. In MATLAB, the version release 2020A, you can go to the Apps tab and look for the Wireless Waveform Generator app. Now, this app enables you to generate a variety of waveforms without having to write a single line of MATLAB code. As you can see, multiple standard-based waveforms are available here. The 5G NR, the LTE or 4G, the wireless LAN or Wi-Fi, different flavors, and the Bluetooth low energy. Now we are focusing on the 5G waveform generation. Notice that you can generate uplink or downlink fixed reference channels, or you can use the new radio test models, an RTM. In this case, you're going to choose an RTM. You have multiple options here, the frequency range FR1, which is the below 6 gigahertz frequencies, or FR2, the millimeter wave. You can choose the FR1, and there are multiple standard-based test models available here. Each of them represent different modulation schemes and use of the bandwidth. We're going to choose the 64 QAM full band, represented by TM3.1. In terms of channel bandwidth, as you can imagine, we have multiple bandwidth possibility here. We're going to choose a 10 megahertz bandwidth. And the subcarrier spacing can be values 15, 30, and 60. We're going to choose a 30 kilohertz and choose our duplex mode FTD. Of course, we can do also filtering if needed. Just by setting the parameters and clicking on the generate button, you can see that we can generate the corresponding 5G NR waveform. As you can see, the bandwidth is 10 megahertz as required. And you can see that we have a channel view with the channel edges and the guard band and the transmission bandwidth. And we have a representation of various elements in the resource grid. Notice that you can go to visualize and add other elements to your signal, including time scopes to look at the IQ samples. You can alternatively go to the impairment section and add various impairments to your signal. This is when you are actually modeling the transmission and reception, doing the simulation in software. You can add various impairments as you can see here. Finally, you can export the signal to workspace or to a file to be used for further processing. All right, let's take a look at the second topic, the channel modeling and pre-coding. 5G standard, one of the first things that was published with 5G standard was the 5G channel models. These channel models are introduced in a technical report 38.901, and they allow you to have a very rigorous spatial channel modeling characteristics for your MIMO channel models. Essentially, we have not only we have the traditional channel modeling profiles like delay profiles, the TDL and CDL profiles, and delay spreads, and the essentially impulse response and Doppler shifts. We also have an antenna array geometry specifications that enable you to figure out when a beamform signal is transmitted over the air, what is the effect of scattering and all other channel modeling based on the clusters that we see at the scattering locations. So 5G allows you to specify a very good channel modeling specification for MIMO and beamform based transmissions. There are other tools in MathWorks. We have communication toolbox, our base product, as well as phased array system toolbox that provide much more support in terms of propagation channels. We have free space path loss, which can be used for large distances, RF attenuation due to atmospheric gases and fog and clouds, MIMO multipath fading channels. We have a linear 2 fading channel models, and scattering MIMO channels, which allow you to specify exactly if you know the location of transmitter, location of receiver, and the location of scatterers. You can do it all in MATLAB and find out what is the actual received power signal arrive at the receiver as a result of propagation channel model. Let's look at the MIMO OFDM data flow, which is the foundation of LTE and 5G and other similar things. So you need to, when you want to do beamforming or spatial multiplexing, essentially MIMO signal processing on an OFDM signal, the process is done in two phases, essentially. You have to do what's known as channel sounding to understand the impulse response or the frequency response of the channel. You send a preamble transmitted signal. It goes through the MIMO channel or your propagation environment. It's received at the receiver, and the OFDM signal processing is done, OFDM demodulation, and you do a MIMO channel estimation. At each subcarrier, you perform essentially a channel, you compute a channel matrix, provides a matrix of gains at each subcarrier relating the transmit ports to the receive ports. Now, every matrix using SVD can be diagonalized, and you can find the precoding matrices that can diagonalize your system, which means that if you use those precoding matrices, V in this case, then you can steer your transmission digitally in a direction that enables maximum retention by your receiver. So that's what the channel sounding is. In the next step, you essentially go through waveform generation, and then from the sounding environment, you use the precoding matrix computed, and you compose your OFDM transmitted signal with precoding. All right, and then the MIMO channel happens, the received beam steering and OFDM happens, and again through channel estimation and equalization, you actually recompute the precoding matrix and either transmit or use that to recover database. This is the process of MIMO OFDM data flow used in 5G systems. So pre-coding plays a big role, and therefore channel sounding plays a big role in successful 5G pre-coding. The practical approach for 5G has been the use of CSI reference signals, and we use the code books to find the best pre-coding vector match at the UE and transmit that in the uplink to base stations so that pre-coding matrix can be used in subsequent transmissions. But this architecture informs how for digital pre-coding